Okay, so for the last video, we went over the basic hydrodynamics of this hydrofoil. It's a very simple hydrofoil. We looked at um, basically proving that from a rough approximation, this would work physically to fly and support the weight of something that was about 200 pounds. Very simplified, just for basic understanding. And what we're going to do is, this is kind of simple arrangement we had, and what we're going to look at is the structure of this, because we talk a lot about the aerodynamic or the hydrodynamics of hydrofoils and things like that, but there's a lot that goes on in the structural side. And we're going to make some simplifications here, just like we did for the hydrodynamics. I'll demonstrate that right now. So we'll take this, kind of move us off the side. We will duplicate our little hydrofoil here from the top view. And what I'd like to do is focus mainly on the front wing right now. We can look at the rear wing later. But we have this fuselage that's being supported. And what I would like to do is just take this wing, kind of cut it in half. Actually, I'm going to do it that way. I'm going to do it kind of like this. So approximately, half. And what we're going to do is we're going to assume that this is fully symmetrical here, which we kind of want a symmetrical hydrofoil, but we'll make that boundary condition of just assuming symmetry. And we'll say this is a fixed. Let me see if I can get the right color here. Let's see that. Not sure why that is not filling, but we will have there we go. Sorry for that. And so we will assume a fixed boundary condition. So you typically see that represented as kind of like slash lines when you're looking at approximations. You see it a lot in textbooks where you have this duplicated, or not duplicated, but you have this basically a stack of lines that's saying, yeah, this is a fully fixed boundary condition. And what that means is that when you look at let's see, let's draw this head on. So we've got a wing. We're looking at some kind of wing, kind of like this size. Actually, let me just steal this. This will be easier. We're looking at a wing from the front, and we're looking at it. So one view is here. We're breaking down the symmetry here. We're looking at the front. So we'll have this mast in the center that's supporting it, and it's probably gonna be a little bit more narrow than that. And then it's going to be supported by the fuselage in the center. But what's going to happen is we're going to get, when we any kind of, we're effectively going to treat this as a beam. So let me make this into a beam, or kind of represent this as a beam. So add a point there, add a point there, and this is going to need to, actually I'll take both sides. Basically, it's going to bend upwards like this, right? Because you have the weight of the rider pushing down on this, and the force from the hydrofoil kind of pushing up on this. And let me try to get the curvature right, at least, where this is going to bend. It's going to be kind of symmetric at the center. So this curvature here, or this angle, is going to be uniform on the sides like that. So we'll represent that, some basic curvature, and it's going to be curving up, and it's exaggerated, but the fact is essentially you've got the water pressure, which before I was showing as a blue arrow. You've got that all along the span here of this wing. And what I would like to do is say that, just for simplicity's sake, this is uniform. And in reality, it's not, because we're taking a lot of approximations this first time around, and it's good to be aware of that. And part of the problem is that when we make this approximation like we did before, we used a simple formula where the coefficient of lift is equal to 2 times pi times the angle of attack of this wing, where the angle of attack we showed before kind of on the side here. This is some angle that this wing is hitting or approaching the water. So that coefficient of 2 pi times angle of attack, that's assuming effectively an infinite wing. It's a very simple approximation, because it's ignoring anything that happens at the edge of the wing here. That's a big problem. Eventually, we're gonna have to deal with that, but in reality, the 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 water is going to be doing something different on this side. It's going to have some span-wise flow, meaning the water is going to want to push towards the edge and roll around, which is why you get these vortices in the wingtips, because there's higher pressure here, there's lower pressure here, and it pushes the water around and creates that tip vortice. And that's why you see a lot of this change in the shape. Either you get winglets or you get changes in the profile at the wingtips to help get rid of this drag at the end. But for right now, for very simplistic sake, we're going to say it's a uniform pressure here. So we're going to assume that for ease of calculation. So we have their weight is equal to 200-pound force. We have the area of the front, which is equal to that. And this is where we have to make another approximation and say, well, the span, we're going to just say the span of this thing is going to be, of the front wing, is going to be 1 meter. Just as an approximation. That's roughly the size of foils out there. Usually they're a little bit more narrow than that, but I think that's mainly for a shipping, packing, and travel constraint. A lot of the boards, in fact, the formula boards were limited to, I believe, 100 millimeters or a meter, just for shipping reasons. And so we'll just show that here with inches, if I can remember my shortcuts. And there we go. Boom. So it's 39.4 inches roughly wingspan. And we have the area. So area of the front. So we'll take the area of the front and divide that by the span. And that'll give us effectively how big the chord will need to be. And we get about 4 inches. So, okay, that's fine. So we have a wing that's 4 inches, a chord of 4 inches, and then a width of almost 40 inches, about 39 inches. So our little sketch here is probably a little bit too radical. So we're probably more like this in reality. So we can kind of shorten that just to kind of get the ratio a little bit more pleasing to the eye. Because we were making a pretty ugly diagram. I want to make it a little bit better. So here's a little modified hydrofoil. I'll probably shorten up the tail too, because we'll eventually get to where we'll want to do something with the tail. But the aspect ratio is a little bit better. It's not quite as huge of a chord of a wing. And so we end up with this chord distance. And then we got to think, what's roughly the size of the width of the foil here? And I know just from looking around, I mean, it's not uniform. The width of the wing gets really narrow at the tip. Again, we're going to assume it's uniform right now, and we'll just say it's a thickness of the wing. And we're going to say that's going to be thickness of the front. Actually, I should probably call this the span of the front, just to be sure. And the span, I have to correct that wherever I change it. And the thickness of the front, we're just going to say it's 1 centimeter, which is going to be, let's say in inches, just for everyone. So 0.39 inches thick. Okay. So that's roughly at the thickest point. And we could go look up cross sections of, things and, look at a whole bunch of data and try to calculate this thing exactly. But I think I'm going to take a shortcut just to, for simplicity's sake, and we will say that we're going to have like kind of a rectangular cross-section wing, because it's not going to be completely uniform at cross sections. Be thicker at the front, it's gonna be thinner at the rear usually to make a good airfoil or hydrofoil. So it's gonna be kind of a wedge shape, but we're gonna take a really first crack and say, you know what, we're just gonna approximate it as a rectangular beam right now. So that's a really rough approximation, honestly. Like it's not great, So if you look at this wing here, edge on, it's kind of look like this. It's going to kind of look like more of a flat plate. And again, we're going to eventually need to correct this. Here, let me drop this line weight here so we can actually see what's going on. So we'll say this line weight is equal to 2. There we go. And I kind of want to get this to be the same. So there we go. So we're kind of looking at our model here. So it's a really thin rectangular beam. And so what we'll then say is that we need our moment of inertia of this thin rectangular beam, and it's going to be 1/12 times the base times the height. So base the front times the height of the front, actually 1/12 base times the height of the the height of the beam cubed, because there's a cubic relationship with that thickness. And we'll say the base of the front, that's the A of the front divided by span of the front. So we already calculated that before. And we will say, well, let's just go ahead and move to a note page. And we'll say that the height of the front, that's just the thickness that we defined it for. And so that's going to be, effectively a centimeter right now. So that gives us a moment of inertia of area, which we can then use to look at in the aspect of this is a beam that's bending. So we get that moment of inertia. And then, so we've got the span. So now we need to go look at a book here that pretty much any engineer should be familiar with. This is Rourke's formulas for stress and strain. And we'll go to the simple case of we have a distributed load. Let's see if we get some camera action that can actually see. Ooh, maybe we can see. I'm holding it to the wrong place. The glare isn't great with this light, but you can get the idea. You look up the formula for a beam in Rourke's, and that tells us with a fixed beam. So really, it's half the span. So I'm just going to say just the half span is equal to span of the front divided by 2, just so I don't forget. And so it says if there's a uniform load on the entire span, then our formulas get really simple. We get our max deflection, which is kind of what we're after, at least from the first respect, is the load per, it's really a function of the load per width, or sorry, a load per length. So W, which is going to be load per length of the front, is going to be the weight divided by span, if I can do that right. So that's span of the front at that first approximation. And that's in meters times Pascal, or really that's going to be in pound force and times inches, right? Sorry, it's going to be pound force divided by inches. It's been a long day. So 5 pound force per inch of span is what this thing is supporting. And another aspect is another crazy approximation, because we're really simplifying things. We're going to say that this is aluminum. And why is that? Because aluminum is a relatively homogeneous material, meaning it doesn't change a lot. Sorry, I wasn't showing that, but aluminum doesn't change its materials property a lot like composite does. It's a lot simpler to analyze than composites. And this is our first approximation. We could always look at composites later. And so we need to know the Young's modulus of aluminum. I went ahead and went to MatWeb, looked it up. It's 10,000 or 68.9 gigapascals. So I can put that in here, let's say 68.9. There we go. And we can also put that in KSI just for English unit's sake. We can kind of look at that. Okay, so we know the moment of inertia of our simplified, greatly simplified wing here. It's aluminum. It's assumed to be a rectangle. Okay, so finally we can compute the deflection of this. And let's see, max deflection. So that is going to be y max, we'll call that, or y at the front, because this is max deflection of the front, and that's all we really care about right now. We will say it is negative times, oops. So it's negative weight of the front times the length. So that's going to be the half span. To the power of 4. So it's a power of 4 with relationship to length. And times 8 times the modulus, which is aluminum, times the moment of inertia, which I did not define as a variable. So we will say I of the front is equal to 1/12 times b of the front times. Sorry, I did this all wrong. 1/12 times b of the front times h of the front cubed. There we go. That's fine. Delete that. We get I of the front. All right, so that tells me right there, what's that? Oops. We get a deflection of the wingtip, effectively. We're expecting in inches. Ooh, so we get about half an inch of deflection at the wingtip from that load. So we're talking, you know, that much deflection. Is that good or is that bad? Not sure yet. Half an inch of deflection, is that going to change greatly what happens to the flow? Is that going to greatly change the shape of the wing? And this is something you have to think about with any kind of problem. You can't just say half an inch of deflection is small. Well, if this was near a gap that was only a 1/4 inch gap or so, this would close that gap. So your model, your idea of reality is just not sufficient to understand that. And now your flow is sensitive to your deflection. That comes up in heat exchanger design and things like that, or any kind of internal flow where a small deflection could actually greatly change your whole flow. Because this is a external flow problem where the water isn't bound usually. You're not usually flying right above the water or the ocean floor or riverbed within like a span. You are close sometimes to the surface of the water, which can matter. But let's say if you're flying this wing right below a very, very flat surface and you're half an inch below the surface of the water, those wingtips would then breach. And so that deflection of that wing would actually affect the whole flow. But that's kind of an extreme case. We'll say maybe half an inch is okay. Maybe it's not. I don't know. I really don't know yet. We would have to go through the rest of this to figure it out. But there is something else that we want to look at, and that is another one of my favorite books. And I'm going to change the view again and try to remember to go back to the composite view here. Formulas for Natural Frequency and Mode Shape. This is Blevins. I actually met the author of this. He is a very interesting fellow. One of my books actually got signed by him. So we'll look at that and we'll say, well, we'll get the same situation where we have a simple beam. It's fixed on one end and it's free on the other, also using the half span, and we'll find its natural frequency. And I'll look at the first modal frequency of the front. So that's F1. We'll just call that F1 of the front. And that's going to be something called lambda 1 of the front. And we take the square of that. This is just a formula straight from the book. 2 times pi times the length, which is going to be the half span, squared. And then all this, you get to multiply, if I do the multiplication right, by the square root of E, which we're saying is, I did something weird there, E of aluminum times I of the front, which is the moment of inertia of the front. And that's going to be divided by M of the front. And it will not compute it because we didn't tell it what lambda was nor what M of the front was. So, excuse me. Lambda is effectively just a shape factor for determining the frequency. And so what that is, so it's L lambda, 1 of the front. So it's for a clamp-free beam, so that's 1.875. There's some more digits there, doesn't really matter. So we got that. Now we have to define M. And M is simply the mass per unit length of the beam. And for that, I need to know what the density of aluminum is. So density of aluminum, I can go back to the website here. And where did we define density? Boom. So 2.7 grams a centimeter. 2.7 gram a cubic centimeter. I need to make sure this is the one thing I don't like about this that MathGuide does, it automatically converts to units. So this one doesn't, and it takes me a little bit to get used to remembering to always hit tab afterwards. So there we go. Hopefully that matches. 0.0975. Yes, it matches. Okay, we're good. So mass of the front. And what that means, there's mass per unit length. So it's a rectangle. So mass of the front, we're going to say that's going to be the T of the front times the, what did we say, the base of the front. And then times the density of aluminum. So that should give us a weight per unit. And bam, right there, we got a frequency that we expect, 32.6 hertz. When this thing is flying around, that thing is going to vibrate at 32.6 hertz. Now that's just a bending mode. And that is a really simple approximation here. This is just this flapping mode of this structure. What that ignores is anything else going on. And I'm only looking at the front wing. This whole thing could basically shake around this mast, right? It could, you could also get a torsional mode. So this really thin shape here, instead of just flapping up and down and moving vertically, it could actually do this whole twisty thing and have this torsional mode like this. It could move like this, but we're only looking at this flapping mode right now. Okay, that's what we just calculated for this really simplistic case, this flapping mode of this. And is this okay? I don't know. It seems kind of low. 32 hertz. Pretty low, it seems. So not entirely sure. We will look at another book by Blevins, which this is the one that flow-induced vibration. I should have it here. Yeah. This one's actually signed by the author, Mr. Blevins. Very nice of him. And what we need to do is look at something called the Strouhal number. And effectively what we have is for various Reynolds numbers, we have various shapes. We have a Strouhal number, which will say we can use to then calculate what happens here. Basically, Strouhal number is a prediction of the frequency of when you're going to get vortex shedding. So in general, a lot of these come down to experimental data, and it doesn't really vary that much. And because we're taking a lot of approximations here, I mean, this is a beam formula for a flat plate. We're ignoring torsional modes. We're ignoring the effect of the wingtips. Our guess here, we just want to be in the right ballpark. We're not going to get this exactly anyways, at least especially at this first approximation. So we're just going to assume of the front, the screw hole number of the front, we're just going to say is 0.2 because it's kind of where you end up with a lot of this book approximation stuff, 0.2. And then you need to know the effective, sorry, I don't mean to wave that around, but you kind of want to know the effective size parameter of what's going on. And it uses D, which screw hole number is usually calculated in terms of a cylinder or a sphere, and it uses a diameter. And so I'm just going to, a lot of the examples are basically your length that's facing the flow. So in this case, it's just going to be this height. What do we say? No, the thickness, sorry. The height of the front or the thickness of the front. So it's proportional to that and the velocity, the flow velocity. So the expected frequency of the flow is effectively or approximately the screw hole number times the velocity, which, what do we say? What do we call it is really the, so we said V, just simply V. In the book it's U, but we said V before. And then it's by the diameter, which we're going to just call the T of the front. And so that gives us a frequency of 89 hertz. So we'd really have to go then and look at a dynamics book and say, okay, so we get a predicted vortex shedding frequency is somewhere around 90 hertz. Our wing is going to shake at the first mode at 32 hertz. Is that good or bad? Again, this is kind of really open to experience interpretation. It could be good or bad. I know that there are some things that we missed here. For instance, this mass for unit span, that's only assuming the weight of the aluminum of the wing itself. And what happens when you get these vibrational problems is that because when this vibrates, it has to move, excuse me, it has to move the water up and down as well with the beam. It's not just the mass of the beam that participates. You get something called added mass of the fluid that causes this thing to vibrate and actually tends to drop the frequency. As it is right now, we may not be too excited by this, but there may be some other mode that gets excited. We only looked at the first mode. The first mode is the lowest in a bending mode. So as we go up higher in modes, it's going to potentially reach a point where this bending mode could be flapped and could be excited by this fluid. And so we could run into this thing vibrating and causing an issue. We didn't look at a torsional mode. Maybe that's closer to this expected frequency. The other thing is that this is proportional to the velocity. And so we're flying around at 10 miles an hour. We get 90 hertz. We fly around at 20 miles an hour. What do we get? 178 hertz. So we start to get in this thing where the range of how this thing is flying than we expect. We expect somewhere around 10, 20 miles an hour, maybe faster. But the faster we go, the more of these higher frequencies that this thing will excite. So actually your speed of this thing traveling through the water will impact how much it vibrates. That's fundamental to a lot of aircraft design, a lot of other structural design with anything that's impacted by fluid. I mean, this could happen in storm conditions with hurricanes. It can happen with a lot of things. Any kind of heat exchangers where you get tubes that vibrate, a machine next to another machine that's shaking another frequency. I mean, that's not a good example of fluid necessarily, but like tubes and tube sheet, when you change the fluid flow in a heat exchanger, it changes the vibrational mode. That's why certain times when you're driving in a car, you get a different frequency, you get a different sound depending on the speed that you're at, and you get that one sound when you have like one or two windows down, and you get that beat frequency in your ear, which is going womp 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 womp. But you speed up or slow down, it doesn't do this anymore. This is one of those flow induced vibration things that's just sensitive to the speed, and it's just something we have to deal with and design around. All right, that's all I have for now. I'm hoping to next we're going to try to model this in 3D very simply, and then we're going to throw a finite element simulation on this. And I just realized I wasn't showing you this, but where we had changed it from 10 to 20 mile an hour. But next we'll throw a finite element simulation at this, and we will try to see how close this gets to our first CAD and finite element simulation, and then try to then pick up and then refine our little hand calcs here and try to get a better idea of what's going on with this design and what is actually important. Thank you all.